evening, Professor. My name is Layla Gomez, and this is my presentation on my baby molecule. So the molecule that I've been studying this semester is PBr3, or also known as phosphorus tribromide, which is made up of phosphorus and bromine. It's a colorless liquid, kind of stinks a little, and in this project, we are going to explore the properties, reactions, and applications of PBr3 with the goal of getting a better understanding of its significance in chemical research. So PBr3 exists in various phases of matter, solid, liquid, and gas, but it naturally is a liquid, colorless, pungent odor, not good. And additionally, this liquid is reactive with water and alcohols. PBr3 transitions into a solid below its melting point of -41 degrees Celsius and turns into a gas above its boiling point of 175 degrees Celsius. So we're going to calculate our fractional abundance of my whole entire molecule. But to do this, we have to break it down. So the first element that I'm working with is phosphorus, and we know this because the first letter of my molecule is P. And what I'm gonna do is you're gonna go to the periodic table and you're gonna find the mass of phosphorus, which is 30.794. Naturally, we have just one isotope, which is phosphorus 31, and it has an abundance of 100%. So for the sake of this project, we are going to make up some numbers. So what I did was I split it up into 90 and 10%, and I ended up with 31 AMU for phosphorus. But for my second element, bromine, we actually have two naturally occurring isotopes, which is going to be bromine 79 and bromine 81. So bromine 79 has a 50.69% abundance with a mass of 78.91, and then bromine 81 has an abundance of 49.31% and a mass of 80.916. And so after we do the calculations, what we do is we multiply the percent by the mass, and then the second percent by the mass, and we get 79.91 AMU for bromine. And so once you look at my calculations, you'll see that they're very, very close, almost exact to what we have here. So now we're going to find the molar mass of PBr3. And then we are going to find how many moles we have in 5 grams of PBr3. So to find the molar mass of my molecule, we're going to take the mass of phosphorus and the mass of bromine, and we're going to add them together. But we can't just take the mass of phosphorus and bromine. We have to multiply them by how many we have in the equation. So we have 1 phosphorus, we'll do 1 times the mass of phosphorus. And then we have 3 bromine, so we'll do 3 times the mass of bromine. And then once we do that and we add them together, we get a mass of 270.79, 270.7 AMU when you do the correct significant figures. So now what we have to do is we have to find how many moles we have in 5 grams of PBr3. So if there's anything that you taught me this semester, it's conversion factors. So what we end up doing is we divide 5 grams of PBr3 by the molar mass of PBr3. And from there, we get 0.0185 grams per mole of PBr3. So by now we should know that my molecule PBr3 or as I like to remember it by, Pabst Blue Ribbon. I'm a bartender, so it kind of just fit. But it's made out of phosphorus and bromine. And so phosphorus has the highest quantum number of 3, and bromine has the highest quantum number of 4. And when you look up the Bohr model for each of these elements, you're going to see that phosphorus has 3 onion rings, which is why the highest number is 3. And then for bromine, we're going to have 4 onion rings, which is why the quantum number is 4. So next, what we're going to do is we're going to find the electron configuration for PBr3, but we can't do it as a whole. Again, we have to break it down. So first we're going to find the electron configuration for phosphorus and then the electron configuration for bromine. So as we should know by now, you look at the periodic table and you go from left to right until you hit the molecule that you're looking for. And we go by the blocks. And so here we're going to get our not too terribly long electron configuration, but there's a better way to do that. So what we're going to do is we're going to get our preferred, which we go to the closest noble gas, which is going to be Ne, and then we're going to finish off that electron configuration to kind of condense it and just make it easier to understand. And then we're going to do the same for bromine. We're going to go across the periodic table until we hit bromine. We're going to get our very long electron configuration, which can get confusing. So instead, what we're going to do is we're going to find the closest noble gas to bromine and go from there. So, my compound nomenclature. Phosphorus tribromide, it's a covalent compound because it consists of 2 nonmetals, because it's on the right side of the periodic table. And based on what we learned in class, the name of my compound is phosphorus tribromide. And the reason that we know this is because I followed the steps we learned in class. So, we know that my first element is going to be phosphorus because the first letter is P. And then we see that bromine has a 3 attached to it, which means there are 3 bromine atoms. So because we see the 3 at the end, we're going to make that prefix tri. And additionally, because it's a compound, the suffix has to be IDE at the end. So therefore, the correct name of my molecule is phosphorus tribromide. And after doing some research and looking at my molecule, this was the same name that popped up everywhere else. So now we're going to draw out the Lewis structure of my molecule. So in my photo, we have the Lewis structure for PBr3, and this has 4 electron groups. And we know this because after divvying out all the electrons to where they need to go and doing the Lewis structure rules, we have a lone pair on phosphorus. And so the electron groups here are the bonding pairs from P to bromine. So we have 1, 2, 3, 4 electron groups. And because we have 4 electron groups, the electron geometry is going to be tetrahedral. Even though the lone pair is invisible when looking at certain Lewis structures, it's still tetrahedral because of the 4 electron groups total. And now the molecular shape is going to be trigonal pyramidal, and that's because of the lone pair on phosphorus. It does not appear as a bond, but it still creates repulsion between the bonding pairs, so it pushes them closer together. And so molecules with tetrahedral electron geometry typically have a bond angle of 109.5, which I got that information from the Vesper sheet that we had in class. However, the lone pair on phosphorus, like we talked about, it repels each other. So instead of being 109.5 exactly, it may be a little bit under, maybe like 102, 103 degrees. And after doing the electronegativity calculations and rules and finding the difference, my overall molecule is polar. We know this because every PBr bond is polar. And because we have, because they're all polar and the shape is trigonal pyramidal, they don't cancel out. So therefore, the whole entire molecule is polar. So now, as stated before in the last slide, the molecule has 4 electron groups. Like I said, because of the lone pair and the 3 bonding pairs. And since it has 4 electron groups, the hybridization is going to happen in sp3. And how we know this is because 2 groups happens on the sp, 3 groups happens on the sp2, 4 groups happens on sp3, and so on with those rules. So there are 3 sigma bonds in my Lewis structure. And we know this because each PBr bond consists of 1 sigma bond. These right here are sigma bonds. Now, if we had a double or triple bond, that would be our pi bonds, but because we don't, we only have sigma bonds. And because all the bonds are single, they're single covalent bonds. So like I said before, no pi bonds. So again, my molecule is overall polar because of the electronegativity rules that we talked about. And this also creates a net dipole moment due to the negative charges that are pointing towards the bromine atoms. The IMFs between the 2 molecules are going to be dipole-dipole and London dispersion forces. And this occurs again because of the trigonal pyramidal shape that we have. And the electronegativity differences, they create a net pole moment. So the positive on the phosphorus is attracted to the negatives, the negative ends on the bromine. And additionally, the London dispersion forces arise in all molecules due to temporary shifts in electron distribution during interactions. So now we're going to compare phases and intermolecular forces to water from our molecule, phosphorus tribromide. So again, at room temperature and its atmospheric pressure, it's going to be a liquid, and that's because of the polarity. So the intermolecular forces hold the molecule together. But water and phosphorus tribromide are similar in that they both involve positive regions of one molecule attracting the negativity of another. However, water has a greater polarity because of the H plus molecules. And so this difference in polarity stems from the stronger electronegativity differences and the hydrogen bonding capability that water has versus phosphorus tribromide. So from here, we're going to figure out the percent composition of PBr3. So again, we're going to find the molar mass of our weight, or the molar mass of our molecule, which we've done before, which is 270.69 grams per mole. And from there, what we're going to do is we're going to take the mass of phosphorus and we're going to divide it by the whole molecular weight, which was, again, 270.69. And then we're going to multiply that by 100, and we're going to do that for phosphorus and bromine. And from there, we get 11.44% phosphorus and 88.57% bromine. And we knew that the bromine was going to be a higher number because we have 3 bromine atoms, whereas phosphorus, we only have 1, so we knew it was going to be a little bit of a smaller number. Yeah. So to get a balanced chemical equation, first we have to start with our unbalanced, which is PBr2, which ends up as PBr3. So to balance that, what we have to do is we have to add a 2 coefficient on the right side, creating 2 phosphorus and 6 bromides, or 6 bromine atoms, I'm sorry. But now this side of our equation isn't right, so now we have to balance that out. So then we add a 2 to the left side on the P, so that way this and this are the same. And then we have to add a 3 coefficient to the bromine, because when we multiply 2 by 3, this becomes 6. So now here we have to have 6 bromine atoms. So then 2 times 3 is 6. And now the equation is balanced, and it makes more sense. Excuse me, that was the end of my presentation. Thank you so much for watching. Have a great night.